those components distribute p phases until a deadlock equilibrium dead end situation is reached, when there's no further transfer of matter between phases, which we call equilibrium. So we said that, well, we can independently specify in each phase n minus 1 components or fractions or mass fractions or mole fractions, what have you, because the sigma has to add up to 1. And so we can do the same thing for every phase. So the total number of equations, variables that we have is n minus 1 within brackets multiplied by the number of phases, which is p. So p into n minus 1. Now I am asking you the question, how many independent equations can we write relating these variables?
Sir, I guess we calculated it as n into p minus 1.
Right. And now the question is, very good, why did we do that is the next question.
So to find out the degree of freedom.
No, no, I don't mean that. What, of course, that may be true. But my question is, how did we arrive at the number that you just now specified, which is p minus 1 into n? How did we actually arrive at that? By what logic did you reach that conclusion?
So we had a discussion that at a time two phases are going to be interacting with each other, and
Right.
using this we came up with the logic that since we have n variables, that is n compositions, that is why n into p minus 1 would give us the number of independent equations in this scenario.
Right. Almost right, but not exact. You see, while you are right in saying that there are these phases, the truth is that the exact reasoning is in the fact that whatever be the number of phases, in this case p, the equations that we write have to deal, all the equations that you have relate to an equilibrium pairwise between the two phases. So you can say the potential of the ith component in phase 1 equal to potential of the ith component in phase 2, and that's one equation. Similarly, you can say chemical potential of the ith, whatever I is, 1, 2, 3, 4 dot n equals to number mu I in potential in phase 3. And so on, you can do it all the way pairwise to n. So now how many such pairings can we do? Yes, it will be n minus 1. And I'm sorry, p minus 1, right? And now the question is, each you can do that I can refer to any of the n components, as you correctly pointed out, Ashiji, and so of course the number of compositional informations that you have is n into p minus 1. Now we define the degree of freedom as the difference between the number of variables that we have minus the number of pieces of information that we have. So we should subtract the equations from the number of independent variables. That, by definition, is your degrees of freedom, capital F, let us say. You can do that. What did you find?
So we get n minus p as the degree
Right,
of
we
freedom
get
in this
n
case.
minus p. Now these relate, when you subtract this, you will get n minus p degrees of freedom, but these are only the compositional degrees of freedom. They only relate to the concentrations, right? We only when you change the temperature or you change the pressure, then you will have a separate degrees for them. So you have not included the temperature and pressure degrees of freedom in this. So you have to add both of them. So therefore, Gibbs added to n minus p. He added these two to account for changes in T and capital P. And so therefore he said that the degrees of freedom capital F is n minus p plus 2. And this is a very general rule as long as we have phase equilibrium in operation. Pratham, am I clear? By the way, every abbreviation reminds me of something. Like PB is Poisson-Boltzmann actually.
Yes.
There's a Poisson-Boltzmann equation actually. But unfortunately, I can't use that. So this is a first oneself. So let's ask Pratham. Let's ask Pratham first. So is that clear? The logic? The
Yeah,
number of
yes, sir.
degrees of freedom is, as Ashi said, n minus p plus 2, a very, very general phase rule. First proved theoretically by Gibbs, of Gibbs free energy fame. Am I okay, Pratham?
Yes, sir. Yes.
Right. Very good, very good. Now, you can apply this to essentially any problem as long as we have liquid vapor, solid vapor, liquid, etc. equilibrium, right? I mean, if you don't have equilibrium, obviously the compositions will keep changing. So, no specification, no such rule can be proven. So, suppose since we finally want to go to steam, a very non-ideal system, let us take a simplest possible case. And actually, we want to do quantitative calculations. We are not there yet. But let us qualitatively, if I were to tell you a very simple, common sense type of system, water in equilibrium with its vapor, liquid water in equilibrium with its vapor. For this, how many degrees of freedom will that system have? Incidentally, another question, everybody shows up here as abbreviation, no VK, HG, PB, DP, SR, but there is also a dot on the right side. Some are in red, others are in yellow, some are in green. What does that mean?
So it's like, it's a feature, like it's the availability of the participant. So if it shows like a yellow, like you can basically set it to whatever you want. If it shows a yellow, that means the participant isn't logged into Teams. If it shows a red, that means the participant is like already in a meeting. And if it's a green, then it shows that the participant has logged into Teams but isn't in a meeting.
So what does that mean? I mean, if Saurabh Raj is in green, it means what? He's there or he's not there in this particular.
So it means that he is logged into Teams, but he isn't attending a meeting. Like it's
This
like you
meeting.
can, so you can set it to basically whatever you want. It's
why should I set it? I mean, so is he,
no,
for instance,
like
if I ask Saurabh
I
this
meant
question,
a person can set it to whatever he or she wants.
so Saurabh, that means he's not available here?
No, sir, it does mean that he is available, but like he set his status to available.
I see. Okay, let them. Anyway, let us worry about the question I asked, a common sense question to which we can apply what we just derived.
So it has to be, it should be one, right?
Right, it will be one because the number of phases is two, one liquid and one vapor, and there's just a single possible single species, the simplest thing one can start from, which is water. So if I apply that, then I will get 2 minus 2 plus 1. So I just get 1 degree of freedom. So, but what does that mean as far as the properties of this system are concerned?
So like to find like the final equilibrium concentrations or like status, we need one more physical parameter to be specified.
Right. So we only, what you mean is, if you want to find the changes with respect to a suitable reference in any thermodynamic property, you need to specify only one parameter of state. For instance, if you, for instance, specified the temperature, or if you specified a given pressure, then you know from our daily experience that water has just the same boiling point, right? I mean, so once the pressure is specified, everything about the system is specified, its boiling point is specified, and I don't need to specify both, because specifying one fixes the other automatically. And not only does it do that, but if I have this two-phase system, it will also specify for me the enthalpy that 1 gram or 1 mole of vapor carries with it at under these conditions of temperature and pressure, and also how much in the liquid, because the liquid enthalpy should be much lower per gram of liquid that is present, how much of enthalpy that has per gram, and then the net enthalpy of the composite system of liquid plus vapor, which I can, if I know the fraction of the system that is vapor or liquid, whatever, then I can calculate the total enthalpy per composite 1 gram of per 1 mole of the system. So I just need to specify one intensive property, and that's it. Then everything about that parcel of steam or parcel of water in equilibrium with vapor is fixed. Okay, let us take something else. Um, suppose we take water. Suppose we take water at its triple point. How many degrees of freedom does it have?
So zero.
None, right? Because I have three phases out there, and I have a single component, and as long as I don't add any other component, and all these three are existing in equilibrium, right? So I have 1 minus 3 plus 2, so I have 0 degrees of freedom, and that's about the minimum number of degrees of freedom that any system can have. That means that there is everything is specified, and for water, unless we add an impurity or add some other component to it, for pure water, I just have, I mean, whatever 0.01 degrees Celsius and 0.006 atmosphere, that is a fixed point. And only if I change these conditions, if I change any of these pressure or temperature, then I will deviate from that triple point, and one phase will disappear, at least. Right? So we probably need to look at that phase diagram on a PV. We can do it on a PV diagram or a PT diagram, but probably I will leave that to Monday, I mean, or to after minor. Otherwise, people will lose me when we discuss all the steam business and start doing calculations. Okay. Now, suppose I tell you that the mass fraction of the steam in a two-phase system, that is, it has liquid water in equilibrium with vapor, the case we just did. Suppose I tell you that the mass fraction of the vapor in that two-phase system is small x. Then how would you find the entropy, enthalpy, internal energy, specific volume per unit gram or mole of that two-phase system?
So do we just find the required parameters for like each specific phase and then multiply it by the like mass fraction, and then
Right.
add
But
them.
the question now is, you know the mass fraction, small x, but now the question really you have to find out is, how do you find out, how do you determine what you have to multiply it with?
So won't it already be like calculated?
Well, the word calculated, I am afraid, is the wrong word, because you have to
Like
calculate it. But yeah,
observe.
the data to calculate it is will definitely be tabulated, because we are dealing with steam, highly non-ideal system, but whose properties have been experimentally evaluated and tabulated in tables of steam by the mechanical engineers, and over during the revolution, industrial revolution, and perfected to decimal points since then. And now every thermodynamic book would have these tables, or it maybe you can also, it could be in chart form of charts. Normally they are tabular in the form of tables, but now you told me that there is only 1 degree of freedom. So how should we actually do it? How should we actually get this number, or say enthalpy per gram or per mole of this parcel of steam, this parcel of liquid water in equilibrium with its vapor? I'm calling, generally there's a name for that. We either call it saturated steam, or we call it wet steam, which means that it's a two-phase system. So there is a wetness to it. That is, there is liquid water in equilibrium with the vapor. So it's called wet steam or saturated steam. So for this parcel of saturated steam, how should we actually go about doing the calculation, assuming that all the properties of the single phase systems are known per unit volume, or per unit mass, or per mole, or whatever, depending on where, how the data is tabulated? So what you will do is, you will take that single variable. Suppose, what do you want specified, temperature or pressure?
So I guess temperature.
Okay, doesn't matter. But suppose you know temperature. What you will go is, you will go to these tables of the two-phase steam, or wet steam, or saturated steam. Different names are used by chemical and chemists and mechanical engineers. You will go to that temperature. You will read the pressure that is fixed, because you told me 1 degree of freedom only, so the pressure is fixed. So for that temperature, the pressure will be automatically tabulated, right? So that you know the total pressure of the system. Very good. And now what that table will also tabulate for you is the enthalpy, entropy, internal energy, volume per mass, per unit mass of the vapor, and per unit mass of the liquid, because they will be very different. I mean, in general, if you wanted to idealize it, you could take the specific volume of the liquid to be almost negligible compared to that of the vapor. But why should we do it? We can exactly calculate it, since you have the number. But maybe we can't do the same thing with enthalpies, perhaps, but maybe we can do it with volumes. But why should we do? We have the specific volume per unit mass of the liquid, specific volume per unit mass of the vapor. We have the enthalpy per unit mass of the liquid. So you will read at that temperature the capital pressure, the total pressure on the system. You will also know what is the specific volume of the gas or vapor, which let us call that V subscript G. You also know the specific volume of the liquid, V subscript L, per unit mass of the liquid, so much meter cubed it occupied, or so many centimeter cubed per mole of the liquid. So that same thing, H subscript G, which is the enthalpy of the vapor per unit mass, and you also know the enthalpy of the liquid, H subscript L. Normally we use small l's when we specify small case variables, when we are specifying per unit mass or mole, small h. So small hl and small hg. Similarly, S subscript G and S subscript L for the entropies of the liquid and vapor phases, and the internal energy also, or we can calculate from the definition of U from small h, and knowing temperature small h, S and small h and applying the definition of enthalpy and internal energy. So you know now all of these quantities for each phase, and now since the mass fraction is given to you, you will just take the weighted average of it, and so you will take S. So the enthalpy of this parcel of steam per unit mass of the steam will nothing be but small x into Hg plus 1 minus x into Hl. Similarly, the specific volume of the steam in centimeter cube per gram of that steam or of that two-phase system will be V subscript G into X plus 1 minus X into V subscript L, and so on for all the other properties. And so you can calculate enthalpies of that steam, two-phase steam or two-phase liquid vapor equilibrium water at any temperature or pressure. Am I all right?
Yes, sir.
You're okay with it? All right, very nice, very nice. If you're okay with it, let us go ahead. We can keep on, as in one nice thing about this course is we can keep on moving from one to the other, and then there's no end to it. Only our time puts a stop to it, and your patience and how soon you get fed up with this professor. Okay, or with the sound of his voice. Unfortunately, you can't see me, and so it's only the voice that is you have to hear. So now, if I may be a little funny, and you can all have a laugh. So now let us say, I start heating this two-phase system, keeping the pressure constant. Let us say, I can do that, no? Why not? I can keep the total pressure constant or keep the total temperature constant. No, I don't want to do that. Let's keep the total pressure constant. And I start heating this system. What do you think is going to happen, Devpriya? Gradually, this liquid part is going to get converted. Don't you right? Don't you think so?
Yes, sir.
So it will become vaporized.
Yes.
So initially, let us say I had a single phase system of liquid water, and at a constant pressure, if I heat it or if I keep the overall composition at constant pressure the same, I can keep heating it till that single phase liquid water becomes a two-phase region, which is what we started with in problem number 1. And now as I further keep heating it, there will be a separate liquid curve and a vapor curve, and slowly the last drop of liquid will be eliminated and will basically get conjoined with the vapor, so that I have a single phase system and I have only vapor. So now the two-phase system has got converted to a single phase system, correct? Are you with me?
Yes, sir.
Wonderful. So this we will refer to as superheated steam or superheated substance, meaning you have converted that two-phase system into a single phase and the last droplet of the liquid has disappeared. Now, suppose I were to tell you that the last drop has disappeared and now this parcel of steam is superheated. How many degrees of freedom does it have?
So 2.
So 1.
2. So now, how many independent parameters do I need to specify to
So
fix
2.
the state of this steam?
2, right? Because
2. So generally,
temperature
let us
and
say
pressure.
that just giving the temperature is not enough anymore, because you lost some information when you transform that into the vapor. So you will have to give not only the temperature but also independently specify the pressure. You're not going to have the same thermodynamic property irrespective of the pressure at a constant temperature anymore. So now I need to specify two quantities to fix the state thermodynamically of this steam. So so this I have called the superheated state, and let's call the degrees of superheat as the temperature to which you have heated this system above the saturation temperature, which is the temperature at which you have saturated steam, because that you told me at a fixed pressure there's only a particular temperature, right? So I can specify that saturation temperature, and let us say I go 50 degrees above it, then degrees of superheat is 50. If I can go 100 degrees over it, degrees is 100. But each of them is going to happen at a different pressure. The pressure will also simultaneously keep changing. All right? Okay, yeah, you are with me on this. This is a very nice class. So I mean, just 4 students, and we
Yes,
everybody is
sir.
agreeing with me. Wonderful. So we can go next to the next thing. Can we?
Yes, sir.
All right.
Yes,
Let's
sir.
now ask you something little tougher.
Yeah.
कोई मजा नहीं आ रहा. Let me frame it. Very nice. So you know now what the saturated steam is, what the superheated steam is. Now let us say that I start with, suppose I have to find an enthalpy change in a simple heating pro or some kind of process. We don't know what the process is. Could be isentropic, isenthalpic, isobaric, or isothermal. Well, no, I don't want an isothermal in this case, or an isobar, because I'm going to change these conditions. But okay, I can have any of these variables, or I can change all of them, T, P, H, etc., etc. Let us say initially, let us say I was in liquid water. Let's simplify it. Let's not leave everything unspecified. Initially I was liquid water, so very easy. It's liquid. I just go pure liquid. So I go to the water, the L subscript part, and I can find specific volume at that temperature and etc. I mean, and the pressure. I can find everything of that water that you know how to do from your previous knowledge, also from this class. Now let us say I heated it up. I heat it. My question to you is, and somebody asked me, I want the final state of the steam, but how do I know, or how do I determine rather, that's the word I was looking for, how do I determine? You see, I do not know a priori when I heated it whether what my final state is, right? Is it a state of two-phase steam, saturated steam, or is it a single phase superheated steam? So my question to you is, of course, enthalpies of a superheated steam will be even higher than that of the saturated steam, right? Because you have given increased temperature, and as you know, it is an increasing function of temperature. Only for of course, its pressure is also changing. It's not an ideal gas, so it's not just a function of temperature. The internal energy will, however, increase with both temperature and pressure. So unlike in an ideal gas, it was solely a function of temperature, but it will also change with pressure. So all of these could be changing in a single variable, single phase steam. Now, how are you going to determine if the final state of the steam when I heated something from liquid water is a saturated steam or a single phase superheated steam? Because the enthalpies will be very different for these two cases. So will be the entropies and the internal energies. I mean, the internal energies of the saturated steam will be, even if it is just a vapor and there's an incipient saturated steam where the just the last droplet of liquid is just alive, it will be much lower than if I were to heat it beyond that till it disappears and then further heat it till its enthalpy internal energy increases. How would I know what the final packet of steam looks like, or how will I determine it, assuming of course that I have all the properties before me, of you have the tables, right? I mean, I think that's something that you will need to have, because then I don't need to give you all the thermodynamic properties every time. I don't need to give you enthalpy at a temperature, entropy at a temperature, internal energy, volume, everything you will pick up from the tables. We just have to, and we are not using any equation of state. We are not making any assumption of ideal gas or ideality anywhere, right? We are taking exact values determined experimentally. So how will you determine whether the steam is a single phase steam or superheated steam. I'm sorry, double phase steam or superheated steam. A more interesting question than the ones that you have already solved. A priori, I haven't specified to you when I heated it what my find whether I didn't tell you it is saturated or it is superheated. So how will you going to find out?
So we can just compare like the measured enthalpies and the observed enthalpies, right? Like from the table. Like if the observed enthalpy of the mixture, like the phase that we have, is nearly similar to the enthalpy of pure like superheated steam, then we can say that
Okay, but
possibly
that
this
would
is
be, you can only do that provided, suppose I ask you to find the final enthalpy, you don't know what, you don't know that. See, the experimental values at all temperatures, pressures are available to you, but what you don't know is what I suppose I ask you find me the final enthalpy or final internal energy, what have you. Then what will you do? Okay, if you had that value, you could maybe do the exercise you suggested. But let us say that that is what I have to determine in the problem. I mean, I have to calculate that. Why not? That is a very common.
so
That is
like
what. Then
maybe
what will
then
you
measuring the volume or something.
do? Even let us say I ask you to find the final volume. I can do that. Why not? Let us say I ask you to find everything of the final steam.
So like then what information are we like originally provided with? Only the
You
temperature
are
and pressure.
provided originally with what it was. It was pure liquid. And then you have to tell me what you, let us say you are provided with temperature and pressure both. Okay, in both, in initially, finally. Let us simplify it. Let's say you are given initially the water, you are given the T, the P, and then the final you are given some state which you don't know, and you know you are given the temperature and the pressure. So let's, now what will you do? How will we know? When you took that pressure and that temperature, how do you know what the final state of the steam is? Did the last drop of liquid disappear or it was still there? How will you find out? More challenging question. You'll have to think a bit, my dear guys, boys and girls. If you answer this immediately, I will come up with the next one. So there is no end to this. Anyway, we are close about time. Time is running out, but you have to. I think you have to put in. It's not something as. I mean, you answered very nicely until now. So of course, I want to always show to you that there is another question that will require some more thought. So what we have tried to do today is to do away with this whole assumption of ideality. We are not going to use ideal gas and ideal liquid or any of those Raoult's law business. I'm fed up of it. We did enough at school. Systems are not ideal. Certainly in industry, systems are not at all ideal. And we have to now do exact calculations. Now I said you can do that for any substance provided you have data. You need a lot of information. So I said, well, let us do it for steam, which is a wonderful system.
Excuse me, sir.
Yeah.
Sir, but we can use Van der Waals equation of state, right? Which is like the ideal gas
Approximation, my
equation.
dear boy. Only a very poor approximation. Van der Waals equation only works for a Van der Waals type gas. It doesn't work for a vapor. It doesn't work for a two-phase system, and certainly it is a very poor approximation for any real system. All of these, of course, their Van der Waals equation has also been supplanted, and today we have a lot of cubic equations of state. They may be a little better, but you know what? They are all poor. They work at very low pressures. Around 1 atmosphere, they may work. The moment you increase pressure beyond 10 atmospheres, you're finished. All of them start deviating from the actual experimental values. And if you pressurize a system, like you go a little bit into the earth, or you build a high pressure vessel like in a chromatograph and go to 100 bars, you're finished. Your Van der Waals gas and all, you can simply forget it. If you want to measure something in the upper atmosphere, or you where the pressures are low, or if you want to measure something in deep into the earth's crust where the pressures will be 500 bars, you can forget about any of these equations. So we don't want to use any of the regular equations of state. First of all, they are only valid for gaseous systems, and they are certainly not valid for wet two-phase systems, including steam, right? So that's one thing that we have done, and we tried to understand how the phase rule is derived in general. We really discussed at great length in 2 classes how we should define the number of independent equations that we can write and how many independent variables that we have, and we derived it from first principles. From that, we came to the concept of the degrees of freedom. We applied it to some simple common sense problems that you are familiar with of water boiling, etc. And you found that it's agreed with what your common experience says, day-to-day experience tells you. And then we applied it to a triple point, and then we started, kind of complicating the thing and going to a saturated steam and then superheating it. And now we have to come to the problem how to determine is the steam saturated or superheated, which I didn't tell you, right? So that's really what we should start with. Okay, that's where I think it's a good place to stop for the moment. By the way, you guys were to make project pairs, and that's why Monday was given to you. It doesn't look that much progress has
So,
been.
I had a question, like, what exactly are we supposed to do for the project?
That is up to you. I mean, that is for the group to decide. I'm not going to.
So, but like,
Uh,
at least, like, uh, give us some sort of idea,
that is your
what are we supposed
that is
to?
your lookout. I mean, that is completely left to the initiative of the group. I mean, I don't want to specify. In general, I do not like to micromanage or specify things. I mean, I used to do that when I was a younger faculty, perhaps, but then, you know, I went away from this. I'll tell you why. I mean, maybe you're too young, you won't understand. And generally, I mean, second year, first semester is very young group of students with very little experience of things, right? So, what I found is that too many of my ideas were all the time being, what is the word, injected into the students. And around when I went abroad for my first sabbatical leave to Japan and Germany, I said ऐसा नहीं करना चाहिए. So when I came back in 2006, I changed my approach completely. Of course, this was not the most productive way because students are also, not independent and they are dependent. But then, I said, we cannot keep on forcing your ideas. So I do not have any idea what you should do on this 20%. I mean, I have a good idea what you guys need to do for the minor and major, perhaps, and I tried to tell you. But obviously, we are going to ask what we have done. So we are going to ask some calculations on mass balance, and perhaps if I want, I can set something on what I have done. I haven't decided. The last couple classes that will be a bit harsh, perhaps, for the other students who have not attended. But really, I do not have any conception of what you should do. Yeah, hundreds and hundreds of processes in chemical industry and chemical process systems and bio industries, and you're most welcome to do a balance on any of these. I mean, it's for you all to. And I'll just sit back and listen while you give a 10-minute presentation. So, okay, guys, good luck. We meet on Sunday. Am I right?
Sure. Yes,
Sir,
sir.
sir, could you share about something like what is the pattern of minor and syllabus for that?
The whole thing, whatever we have done, I will definitely ask you to calculate something. Definitely. I mean, it's a calculation course, so you expect some material balance problem. There are so many. I mean, but yeah, I won't do like last time where I gave a problem which couldn't be solved in 1 hour. So this time maybe I will err on the other side and may become too short. I don't know. I can't
Sir,
evaluate anymore how fast or how
Sir,
difficult.
what
What I
is
think is
the
difficult, you guys find difficult, easy, and what I think is easy, you guys find difficult. So God only knows. So
sir?
we will err on the other side this time.
Sir, what is the timing for the minor?
I don't know. I thought you would tell me.
Sir,
I think it's on
sir, it is given
8th November.
12:30 to 3. It is given 12:30 to 3 on 8 November. So, so that is the time slot
12:30.
to 3.
Okay, so we should
So,
do it at 12:30, no?
uh,
Or
sir,
should
can you
we?
like we So we also have another exam in the morning. So could you like shift it to a bit later in the 12:30 to 3 o'clock slot?
Problem is then we don't communicate it to anybody. It becomes a headache, no?
So you can send a mail.
Yeah, but I think see, this is not something for which you have to study.
Yeah, so that's right.
So, but what will be the platform like? Where will you conduct the
So
minor?
yeah, because those instructions are we need like how to submit and where to submit, and so if you could send a mail regarding all those things.
Also, so you muted like.
This is the first time I am setting something. So why don't we make it objective then? You said that's you can do that on Moodle. You told me, right?
Yes, sir.
Yes, sir.
Yes.
So I can always give you options, no? A, B, C, D, E, F, G, or
Yes,
something,
sir.
and you can choose. That's not a problem, right? But still, you will have to calculate to get that, and then you just need to submit me that option. Is that all right?
Yes, sir. It works with everyone.
That is
Yes.
okay. So let's do like that. So you will calculate whatever in that 1 hour, and you will come up with an answer, and you will choose the answer closest to what is there in the alternatives. Looks like a
Yeah.
very doable thing, right? I will let's do it like that. I let's see then. If that doesn't work, next time I will give you a more qualitative. I mean, where you have to actually write and upload the things. I don't know.
So,
This
sir,
is my first time doing online, so I don't know.
sir, please send a mail regarding the timing so that everyone knows what the timing is. Otherwise, they won't.
Well, Devpriya will send it 12:30. I think we should do it. I don't want to leave it to the end, and then somebody says we have some other exam and we are short, and let's do. We are meeting at the initial the left hand interval of that slot. That is.
Okay, sir.
Yeah, so it will be 12:30. So I don't need to. I mean, they are all supposed to show up. You're not. I mean, JEEs and other exams, you're not allowed half an hour later, right? So you're supposed to come.
And so the duration will be like 1 hour, right?
1 hour? Yeah, 1 hour.
Okay.
That's it. Yeah, definitely 1 hour. All right. So we meet at 12:30, and you can put in the punch in the correct objective, correct alternative, and we will follow the pattern. You don't need to upload because anyway, as I said, I expect that you will all try to solve it, and that itself gives you some 50% of the marks. Okay, thank you. Good luck.
Thank you,
Talk
sir.
to you.
Thank you, sir.
Right.
Thank you, sir.
Thank you, sir.
Thanks. Most welcome, Ashi.